Hey, Katie.
Hey, Ben.
Do you follow our Twitter account?
I do, loosely, not as closely as I should sometimes. But
Yeah.
yeah, there's some good stuff on there.
Yeah. Someone was mentioning, this person tweeted, enjoy the multi-level modeling, but how would it compare to a decision tree? And I was wondering, I have no idea what that means, but I was wondering maybe if you do.
Yeah, so this came to us from Rajiv Shah. And I thought this was a really interesting question, and I could not answer it in 140 characters. And so let's just take 15 minutes.
All right, that sounds good. You are listening to Linear Digressions. All right, 15 minutes. Let's go.
Multi-level modeling, we talked about this a couple episodes ago. If you haven't heard it before,
That was radon, right?
yeah, we were talking about radon and how there's radon in different states and how that's an interesting analogy for elections, if you want to think about it that way, and why they use multi-level models for election forecasting.
Yeah,
And
that was a cool show. You should, if you haven't heard it, you should go and take a listen.
oh yeah, it's super cool. Multi-level models are really neat. But a lot of these multi-level models, they're assuming that the underlying model is going to be something like a linear regression or a logistic regression, which a logistic regression is like you take a linear regression and you turn it into, instead of having a continuous output, it has like a 0 or a 1. So it's like a classifier instead of a regression. Decision trees, though, are an entirely different kind of model type, or algorithm type, I should say. And we haven't talked about them a whole lot on this show, but let me just very quickly give you an idea of what a decision tree will do. Let's imagine that you only have two variables in your data set, and you're trying to predict some outcome. You're building a classifier based on those two variables. So a decision tree is going to pick one of those two variables, and it's going to apply some kind of Boolean cut on that variable and all the things that sort of the answer to, is this value, let's say, less than some threshold? If the answer is yes, it goes to the left. If the answer is no, it goes to the right.
Right. So basically, you're taking that whole range of values and you're reducing it just to a simple yes or no.
Exactly. And you can do that repeatedly, so you can have multiple different types of thresholds sort of that are all operating at the same time.
Oh, interesting. So like on the same range?
Well, so you could say something like, it would be fairly straightforward to have a decision tree that says something like, let's say you have all of the even numbers end up being classified as yeses and all of the odd numbers end up being classified as no's. You could have that in a decision tree.
Oh, I see.
Where you have it sort of like yes, no, yes, no, yes, no. But you have potentially many different variables that you can be splitting on one after the other. And so they can start to have, one of the things that's nice about decision trees is you can have the correlations between variables can start to get captured a little bit. So if you say something like, well, white women feel this way and Asian men feel that way, then what that's going to look like in a decision tree is first you're going to split on gender, and then you're going to split on race, or first you're going to split on race and then you're going to split on gender, so that you can have each of these buckets that you end up that have both race and gender that you're aware of in them at the same time. It's a very different algorithm type, and in the course of kind of thinking through my thoughts on this, the reason I thought this was a really interesting question is I was like, a multi-level model is often used in something like social science, or maybe you could imagine some kind of physical science. It's used by statisticians or practitioners of other fields who very often have pretty good understanding of the system that they're trying to model. And so you imagine that there's some black box, and we call it the world. It's nature. It's the American electoral system. It's sociology or whatever. And that takes in certain kinds of inputs, like what is your race and your income and your gender, to take a sociological example. That gets kind of digested by this data generating process, and it spits out some kind of answer about who it is you're going to vote for. And so each one of us has this internal little black box that turns all of our attributes into decisions that we make in certain situations. And what you're trying to do very often when you're a statistician or a researcher or some kind of academic person who's trying to study these systems is you want to understand that internal little engine that creates the dynamics.
So you're trying to understand the black box, if you will, that is the person.
Exactly.
And what of these different, many, many, many variables, only some of which you have access to, how do those variables affect things like who you vote for?
Yeah. And so with something like a linear regression or a logistic regression, the answer that you get is going to be a list of the coefficients that multiply each of the variables that you're putting in there. So how much weight do we give to your race? How much weight do we give to your income? How much weight do we give to your gender? Are those weights statistically significant? Are we sure that they're not zero? They're inconsistent with zero, so that means that they make a difference. And so we're starting to describe that underlying process when we run a regression in one of these sort of researchy statistical fields. And that was the way that a lot of statistics and research was done for 100 years, was we're really trying to understand the data generation process. And we're trying to use that to describe sort of the way the world works, which is a little bit more grandiose than maybe sometimes these guys would try to claim. But it's the idea is that you're trying to get a fundamental understanding of what's going on. I'm going to contrast this then with something like a decision tree or a neural network. And decision trees and neural networks, they came a little bit more out of the field of computer science, where these are people who don't have a whole lot of experience explicitly in something like how does your race or your religion or whatever affect your feelings about things. They don't know. And it's not that they don't care, but what they're trying to do a little bit more is not describe that underlying data generating process, but they're trying to make predictions that are going to be as accurate as possible. And that sounds like it would be the same thing, but in practice, it's not. You can have models that describe the data generating process, but very often they're not going to give you predictions that are quite as accurate as if you just try to model the predictions directly. And that's what neural nets and decision trees do.
Oh, that's interesting. So, in other words, if your ultimate goal is to model things the best that you can, why not just try to model things the best you can, rather than taking this very specific approach of trying to model the source in order to understand the outcome?
Yeah, exactly.
So it takes off the restriction of we're going to approach the problem from this direction.
Yes. And so this is something that I think is really interesting in the work that I do now. When I was working in physics, there was a lot of emphasis on the black box, the data generating process. And that made a lot of sense because we have laws that describe physics in a way that are some of the more rigorous laws that we have available to us, like physical systems just are describable with math in a way that many other systems aren't. So physics, I think, is one of the exemplars for looking straight at the data generating process. But that having been said, more and more physics is moving towards the let's try to just model the outputs, and as long as we're getting the outputs correct, then maybe it's not crucial that we understand every single detail of the data generating process. And in my work now, we lean much more heavily on machine learning models than on the data generating models, although we still have a healthy dose of the data generating models, like a very healthy dose. So I wouldn't even say we lean more on the machine learning. Let's say it's 50-50 or so. And so I get to think about both ways of thinking about it. And so the thing that I was thinking about when I was reading this paper, it's called Statistical Modeling the Two Cultures. And it's by a statistician. It was written about 15 years ago by a statistician who was at Stanford. And it's really interesting because you can see that in this paper, machine learning hasn't taken the world by storm the way it has right now. But this guy, he's got a background in statistics. And so he's been sort of brought up in this statistical paradigm of we model black box processes. We're trying to understand the data generating. Building a decision tree is not a particularly principled thing to do. It's just trying to describe the data. It's not really trying to understand it. And that's not what we do as statisticians. And to read this paper, he's talking a little bit about how he leaves academic statistics for a while. He does some consulting. In consulting, they're much more interested in getting the right answer than in trying to understand or convince themselves that they understand the underlying processes. And then he starts to, with this sort of more appreciation of the neural network decision tree approach to things, then takes a second critical look at the statistical modeling, the data modeling side, as he calls it, and how there's all kinds of things that when you're a statistician, you might think you understand the data generating process, but there's all kinds of things that can sort of trick you like that, and you might understand it not as well as you think you do. And ultimately comes to the conclusion that the machine learning approach has a lot going for it, and that the statisticians would be smart to take it a little bit more seriously.
That's really interesting. I mean, I guess a lot of the times you're in a particular field, and I mean, these fields can be quite insular, like ideally all these different fields would be very cross-functional, and research and methodologies and ideas and iteration and all that would be shared across these different fields. But the reality is that, if you're in a particular field like statistics, all of the people you're talking to are also in statistics, and you might not be getting input from these other fields, which might have things that apply to what you're doing. So it must have been kind of interesting for him to step away from his field for a little bit when he went to consulting, and then to be able to kind of like to take a step back and try and reconcile like everything he and all of his colleagues in academia know with the realities of the way maybe things are being pushed forward in other fields, and finding that they can learn from each other.
Yeah. And he goes into some detail here on a couple things he's talking about when he says, maybe they've got some good points over there in the computer science department. So some of the things he talks about are what he calls Rashomon and the multiplicity of good models. So in statistical modeling, they like to think that they're sort of mathematically reconstructing the one true data generation process. But as he points out, there's lots of different models that you can get through statistical modeling that all give you similar answers, but they get there in very different ways. And this is very true of the machine learning models as well, but machine learning models embrace that. They don't try to be claiming, truth in a way that sometimes these statistical models sort of implicitly do. And so the fact that you have many different models that can give you the same answer is a big problem in statistics if you're trying to interpret those models a lot and make some claims about the universe as a result of them. And then also talks about Occam's razor, and is it more important to have a model that's simple or a model that's accurate? And in general, just thinking through these issues.
And just to summarize, Occam's razor is if you have two hypotheses, you should generally favor the simpler one because it's more likely to be true because it requires fewer new things to be true that are unknown, rather than the more complicated one.
Yeah. So if you have a simpler, like linear models are usually fairly simple, and that helps you in interpreting them and things like that. You don't come up with some kind of crazy, unintelligible model like you sometimes can with neural nets, to be quite honest. I've never encountered someone who says that they can explain like what a deep learning neural net is actually doing. Like it does crazy things, but we don't in general understand how they do them.
Yeah, we know how to build them, but we don't necessarily know why they do what they do. We just know that sometimes they work really, really, really well.
Yeah, we just know that they're really complicated. And so for any if given choice that a neural net makes, if you were to be like, hey, why did you make that choice? That would be very difficult to answer in a way that it's not difficult with linear models. And then the last thing that I really liked about this paper, and we're skipping over like a lot of it here because the main body of the paper is substantial, but the second half of the paper, the copy of it that I found, is actually, he sent this paper out to a bunch of different statisticians, and he's collecting referee type feedback from all the different statisticians. And so there's 3 or 4 different answers that are being put out by these very, very smart guys, and they're all really good writers, and it's a lot of fun to read. And the first one is by Cox, who I think is the same as the Cox proportional hazards model. You might remember the Cox proportional hazards model. We were talking about survival analysis. Do you remember this? This was a long time ago.
Yeah, this was a long time ago.
Yeah. So Cox proportional hazards model is a particular type of statistical model by this guy, Sir David Roxby Cox. Can you even believe
that is a
name?
heck of a name.
Yeah.
Sir David Roxby Cox.
Oh, I hope he taught at Oxford so he could have 3 Oxes in his name. Let me look this up real quick. Oh, he was at Oxford.
Yes.
Oh, that's awesome. Okay,
man.
So David Roxby Cox of
I just have to say, this man has a huge body of work, and yet the thing you might remember is that this guy's name has 3 Oxes in it.
Yes. And so he's like old school statistics. And so his field is being a little bit like taken to task here. Like, oh, you guys think you're so smart, but like these computer scientists have some pretty good points. And he's like, psh, you don't know what you're talking about. He doesn't say it that way exactly, but he's defending his turf a little bit and trying to point out some flaws in the thoughts of the original author, Leo Breiman. And so it's really, and then, Leo Breiman has sort of has a answer to his comments. And so you get to see a little bit of this referee process at the end where they're all talking amongst themselves about the fact that like statistics is coming up on a little bit of a moment of reckoning, which none of them knew at the time because this was 15 years ago and machine learning hadn't really taken over the universe yet. But you're starting to see the glimmers of it here and watching everyone kind of wrestle with these issues. And it's a really cool paper because first of all, it's very readable. He's trying to make these ideas approachable and as like straightforward and understandable as possible. But then they're also being kind of digested by these very smart people who are trying to figure out what they mean for like the future of statistics and machine learning all these things that are data science today.
Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.